to introduce today's speaker, Professor Eunseong from Physics Department at KAIST. KAIST stands for Korea Advanced Institute of Science and Technology. And he received his PhD from Pennsylvania State University in 2004. And he got Lee Osheroff Richardson Prize in 2008. In 2011, this year, he received Academic Excellence Award from his current university, KAIST. And again, the same year, this year, he received Young Scientist Award from International Union of Pure and Applied Physics. So he will give us about his research on supersolidity in helium. So please.
Thank you for the introduction. So thank you for coming to this colloquium, and thank you for giving me this kind of wonderful opportunity to present my research work here. Can you hear me? Yes. It's loud enough, right? Okay. My name is Eunseong, and I'm from KAIST. The title of today's talk is Supersolidity in Helium. I guess a lot of people sitting here probably have no idea what a supersolidity is. So, sorry, I always forgot to introduce my collaborators. So I put all the pictures in the front page. That's probably I forgot these sort of things. So my collaborator from my group and outside of my group. So this rotation-related experiment has been done in the collaboration with the people from Ligan and concentric rigidity. Experiment has been collaborating with Dr. Keiya Shirahama at Keio University. So this is the outline of my talk, because as I told you, a lot of people sitting here probably don't have any idea about the supersolidity, so I will briefly introduce you about the concept of a supersolidity and also a review of earlier experimental works on this field. Then I will directly move on to the detailed discussion, which is related with the microscopic origin of supersolidity. I mean, whether or not this kind of anomalous behavior, which was measured in the earlier experiment, is due to the supersolid or something else. Then I will move on to my recent research progress, which is the simultaneous measurement, then summarize. Okay, liquefaction of helium brought a completely new quantum world in our reality, and one of the most fascinating examples of this is probably superconductivity. And this is, below the transition, as we can find, the electric current of the red can flow without any electrical resistivity below the transition. And this superconductivity was discovered in 1911, and this year is like 100th centennial anniversary for this discovery of superconductivity. Superfluidity is very similar to the superconductivity. However, instead electrons or Cooper pairs are flowing. Here in this case, atoms flow without any fluid resistivity. What I mean by fluid resistivity is actually viscosity. So below about 2 Kelvin, liquid helium becomes superfluid, so it can flow without any viscosity. So it can flow through even like a small atomic dimensions of holes. That's called superfluidity. And this superfluidity is also found in the superfluid helium, in the helium-3, which is the isotope of helium-4. And fermium, however, they are PA pairing like superconductivity and behaving very similar to the boson and Bose condensate, and showing this kind of superfluidity. However, at much lower temperature. So for helium-4 is about 2 Kelvin, helium-3 is 2 millikelvin. And this kind of superfluidity is also found in the Bose condensed gas. Okay, so here, and this superfluidity is understood as the appearance of Bose-Einstein condensation and showing this kind of probability. since the superfluidity and Bose-Einstein condensation is found in gas and liquid, people probably can ask this kind of questions. Is it really possible? Is it somehow possible to have superfluid in a solid? It seems to me at first glance it's like very stupid questions, isn't it? Because I mean, we all know that classically solid in the solid atoms are strongly localized at each lattice side. How come you have flow and even superflow, right? However, I mean, it didn't take really long for the theoreticians to realize that it is possible to have this kind of superfluidity even in solid. And so the superfluidity in solid can be called and coined by some physicists in early age as a supersolid. Okay, so supersolid does not mean it is very strong, but it means like superfluid or solid, but has a superfluidity. And people realized that at that time, you can have superfluidity in solid helium if you avoid very strong hardcore repulsion potential. Okay, the way you can do it is actually introduce something like zero-point vacancies or other defects like impurities or dislocations and so on. Okay, and well, the most strong candidate showing this kind of supersolidity will be the solid helium. As we all know from the solid state textbook, like Ashcroft-Mermin, solid helium is quite special because it cannot be simply described by harmonic approximation, as we all know, right? That's because of large quantum zero-point fluctuation of solid helium. Okay, so how can you characterize that kind of quantum fluctuation? Okay, that's Lindemann parameter. Lindemann parameter is simply ratio of fluctuation with respect to the interatomic distance. For the solid helium case, so this is the interatomic distance and this is position uncertainty, which is very relevant when you are describing the fluctuation. But it is very surprising. It is surprising because the quantum fluctuation for the solid helium case is very close to the 30%. This was found in the experiment and also predicted in the quantum Monte Carlo simulation. So 30% is quite big because if you think about the classical solid, when the Lindemann parameter exceeds 10%, it just already melts. So solid helium, even though it has crystalline structures and everything in there, like shear modulus and so on, as a solid property, however, it doesn't look like a classical solid because of large quantum zero-point fluctuation. So this kind of solid called quantum solid. Okay? And right immediately after the prediction of supersolidity, Tony Leggett suggests very simple and ideal way to measure the supersolidity, which is basically summarized as the existence of non-classical rotational inertia. Okay, let's take a look at this movie clip here. Okay, so if we think about the ordinary solid, okay, all the atoms are, as we know, strongly localized on the lattice side. So if the objects are oscillating, then the atoms are following this oscillation. Okay. However, if you have supersolid, the fractional atoms are decoupled from this oscillation because it doesn't have viscosity. Okay. So if someone can measure the rotational inertia, then when you have a supersolid, there is decrease in the rotational inertia from the classical value. And that's called non-classical rotational inertia. So if you can measure non-classical rotational inertia, then you can find the supersolidity. Okay? That's the idea. And so in order to measure non-classical rotational inertia, what we use is a torsional oscillator technique. This torsional oscillator technique is not familiar to you guys, right? But but it is very simple. Okay, the torsional oscillator in principle is a physical pendulum that you can find in the freshman physics textbook, right? So since it is a mechanical resonator, right, it has a resonant period or resonant frequency given from this torsional oscillator. So this is a schematic diagram of torsional oscillator, basically composed of two parts, ferrocopper torsion rod and a torsion cell containing solid helium inside. Okay? In that case, you have mechanical resonant period as this equation, which is proportional to the square root I over k. Here, I is rotational inertia of this torsion cell containing helium, and k is the torsion constant of ferrocopper torsion rod. So if you have a heavier rotational inertia, larger inertia, or smaller torsion constant, then you have a slower oscillation. So the resonant period increases. Okay? Good. So if you measure the rotational inertia, think about this. As a function of temperature, when you decrease the temperature below the transition, there is a missing rotational inertia because of the appearance of non-classical rotational inertia. Okay? So you can measure this kind of change in the rotational inertia by measuring the resonant period precisely. And this is a real picture of the torsional oscillator that I used in the experiment. So this torsion cell contains fiberglass, and a typical pore diameter of this fiberglass is only 7 nanometers. At the beginning, we use this fiberglass because we know that from the prediction, if you have a defects or other dislocations, then you have a higher probability to find the supersolidity. Okay? That's why at the beginning, we use the fiberglass in the cell. Inside the cell. And here, this is the central electrode strongly attached to this torsion cell. And this central electrode is coupled capacitively to detection or drive electrode. This is a simple like a parallel capacitor. So if you apply the AC voltage with frequency directly matching to the resonant frequency of this torsional oscillator, then you can trigger the torsional oscillation. And using the feedback loop, like signal from the detection is actually used to drive this torsional oscillator, then you can maintain the resonance. Okay? So that's the simple technique. However, the amplitude that I used in this experiment is on the order of nanometer or sub-nanometer. So it's pretty gentle oscillation. Okay? And you can also change the amplitude of oscillation or velocity of oscillation by changing the applied voltage. Any questions so far? Now, I will move on to the experimental result. So this is first observation of superflow in solid helium. Okay, I plot the resonant period as a function of temperature. Okay, so here this part is, well, since I plotted in the log scale, this is just linear, and upper part is just related with other things, nothing important. But this is just decreased linearly, and if there is no missing rotational inertia, then it will just follow the empty cell background, no trend, right? However, what we have seen is follow the red data with the minimum oscillation velocity. We found that decrease in the resonant period. Okay, that means we have something missing inside the torsion cell. Okay, we have a missing rotational inertia, and this missing rotational inertia, if you increase the AC velocity, AC oscillation velocity, and that total reduction is strongly suppressed. Well, one thing that I want to emphasize on here is we use the 7 nanometer pore fiberglass. So solid helium confined in the fiberglass, 7 nanometer. So if you think about the motion of any kind of liquid or solid, is strongly suppressed. There is no motion because of the same 7 nanometer. So if there is a motion or flow, there must be superflow. You can simply calculate that using the viscosity penetration depth idea or explanation. Okay? Good. So then later, what we realized is actually the presence of this kind of pore porous medium, like microglass, is not relevant to the appearance of supersolid. So what we have done is we have done the experiment, a very similar experiment. So we made an annulus channel inside the torsion cell without any porous medium inside the cell. And do the measurement again. Again, this is resonant period as a function of temperature. If there is no change, it will just follow this line. However, there is a reduction in the resonant period, okay, which can be interpreted as the appearance of non-classical rotational inertia. Similar thing also observed, like when you increase the AC oscillation velocity, the total effect is strongly suppressed. And we also find energy dissipation with this kind of transition, and this energy dissipation similar to this kind of non-classical rotational inertia. If you increase the AC oscillation velocity, it is strongly suppressed. And the lower panel is actually, if you block the angular channel, the flow channel, then the total signal is strongly suppressed. It's just gone. Because this is not the local phenomenon. If it's local phenomenon, the effect must be there. So this is the second experiment. After these two torsional oscillator experiments, there are at least 10 groups reproduce this experimental result over the world. They all find this kind of non-classical rotational inertia function, the reduction in the resonant period. Also, they find a strong velocity dependence. And also they found the non-local macroscopic superfluid. When they block the angular channel, the effect just completely gone. Unfortunately, or probably fortunately, there are other experimental results which are very difficult to be understood with just conventional superfluid scenario. Okay, there is annealing effect. When you anneal the solid sample, the total signal is strongly dependent on this annealing process, and also hysteresis appears with this measurement, and some people report the glassy dynamics. Okay, I'm not going to go into the details on this experiment. However, since this anomalous behavior looks quite interesting, so it attracts a lot of newspapers and also journals. So this is actually published in the New York Times. It's a whole page review article about this experiment. It's quite exciting, okay? And Science newspapers also spare some page for this experiment. Even primetime TV show interested our experimental result. It's quite interesting. Look at, this is a Big Bang Theory, where one of the main actors, Leo, is actually present. Look at this. Okay, my experiment in the seminar. Quite interesting and very exciting moment.
Is it your slide?
Oh yeah, exactly. Look at this. Here, right here. Oh, that's not my slide. He made it by himself. Probably there is, I think, science.
He steal it from here somewhere.
Somewhere, probably. But copyright belongs to the science, not to me, unfortunately. Okay. And also, the microscopic origin of supersolidity is selected as one of very important 125 questions that what we still don't know. Okay. And this 125 questions was selected by the American Association of Advanced Studies by celebrating their 125th anniversary. That's why it's 125 questions. And the origin of this supersolidity is selected as one of those questions. It's pretty exciting. And from now on, I will talk about two interesting experiments showing this kind of thermodynamic signature of supersolid transition, and also direct DC flow through solid helium. It's quite exciting experiment, even though it's not mine. Or those times I have to move to Korea and construct my lab. I spent a lot of times making those kind of dilution constant and so on and so forth, and other people working on this. Okay, So the first experiment is a heat capacity measurement. They report a possible thermodynamic signature of supersolid transition. Measuring the heat capacity of solid helium is extremely difficult. The reason is very simple. A solid helium is insulating solid, right? The heat capacity decays with T cubic power. So at very low temperature, below 100 millikelvin, it's extremely difficult because the addenda heat capacity, like heat capacity cell, the contribution from that dominates over that kind of small heat capacity of solid helium. So what they have done is actually they introduced a single crystal silicon. It's 5-9 grade single crystal silicon and machine it and make the heat capacity cell. It has a really low heat capacity since it is also insulating solid and high thermal conductivity. So they can measure the heat capacity of solid helium, and then the background heat capacity contribution is only 10% of total signal. Okay? So they subtract the divide T cube temperature dependence and find that heat capacity shows the maximum 100 millikelvin shows a peak, and this peak can be coincide with the temperature where the non-classical rotational inertia appears. Okay, so they interpret this result as thermodynamic signature of non-classical rotational inertia, which is the supersolid. Okay, second experiment. This one is quite interesting. So I will spend some time to explain this. Okay, so Bob Harlock and David Ray at University of Massachusetts, they designed a very clever pressure cell. Okay, so usually when you try to find the DC flow, you just directly squeeze the solid helium and see if anything comes out of the chamber. However, what they did is actually they put the fiberglass on both sides of solid helium, and inside fiberglass they have superfluid, and they use the superfluid to pressurize or add atoms from one chamber and measure if there is any flow through this solid helium and change the pressure on the other chamber. Okay? So this is very clever idea. And also, the second part of the experiment, what they have done is they change the temperature by heating one side of this chamber and see if there is any flow through this from the other chamber. This is so-called thermomechanical effect that was first seen in the superfluid helium form. Okay? So usually you expect that because of the entropy, the flow of liquid, right, generated from hot to cold, right? However, if you have a superfluid, then you have flow from cold to hot. So when you hit one side of the chamber, then there will be a drag flow through the solid helium from the other side. So this is two experimental results that I'm going to show you here. Okay, so they add atoms on one chamber, chamber 1. That's why you have a pressure gradient, okay, between P2 and P1, right? And as time goes on, right, the P1, the pressure decrease, and P2 pressure increase. So this is a schematic diagram of that previous experiment, and as you can find, there must be a flux through this solid helium. Okay, that's why you have an increase in the pressure P2 and increase in the pressure P1. And another very interesting observation is this P1, P2 shows a linear time dependence. Okay, this is very different from viscous flow. Viscous flow, the flux will be determined by the pressure gradient. That's why the time dependence must be exponential if it is viscous flow. So this kind of linear time dependence is actually characteristics of superfluid. The flux is only characterized by the critical velocity. Okay, so this is one example of superflow published in parallel. And the second part of the experiment, as I told you, they raise up the temperature of one of the chamber, say T1. Okay, this chamber, okay, heated, and when you have superfluid, if you heat these things, there is a flow from the cold superfluid to here. Then you have a mechanical superfluid fountain, and this is called thermomechanical effect, right? something like this. So here, what happened, when you heat it, there is flow from the other chamber to this chamber. So you increase the temperature T1, so the pressure in the P1, or the pressure in the chamber 1 increases, however, decrease in the chamber 2. So this means there is a flow from this chamber to the other chamber. And this must be superfluid. Okay? This is two very interesting experiments. So far, I tried to explain the existence of non-classical rotational inertia and other supporting evidence for this supersolidity. So far, I think it is quite clear that there is non-classical rotational inertia and supersolid transition. However, as I told you earlier, as I explained to you earlier, right, there are some experimental results in the torsional oscillator, okay, that cannot be simply understood by a conventional superfluid scenario. Okay, that's why people raise the question. Okay, raise the question like this: is non-classical rotational inertia, that interpretation is unique for the reduction of resonant period? Is there any idea, other ideas that you can explain those reduction in the resonant period? That's the question. And so this is the question. And that's why I go back to the basics. I write down the equation of motion for that torsional oscillator, but I assume everything. Okay. So I assume the damping. Also, there is a back action due to the solid helium inside the torsion cell. If solid helium is ideal, is perfectly rigid, then the only solution, there is no back action term, and the only solution, the reduction of resonant period must be coming from non-classical rotational inertia. However, if solid helium is viscoelastic, then you could have different interpretation. Okay? So think about it. If you have a viscoelastic solid and shaking back and forth, then inside solid helium there is a stress built in, right? Because of that stress built in, you could have change in the resonant period as well. Okay? And once more, if you have especially if this back action term, which is directly proportional to the elastic property of solid helium, is temperature dependent, then the reduction in the resonant period can be explained by this viscoelastic solid scenario. Okay?
Excuse me, what was the definition of your G of T?
G over T is back action terms.
Yes, but what's the, can you give the technical definition?
Technical definition. It's a, can explain you now. I think I need to spend some more time to explain this, but I just want to give you some simple idea how I can reach to this conclusion. Okay, can I talk to you later after the talk? Okay, so quite dramatically, this kind of elastic modulus change is observed in the solid helium. Okay, they measured the shear modulus of solid helium by using this PGT, applying the strain on one side. So in between this PGT, there is about 200 micrometer gap of solid helium. So if you apply the strain on one side and measure the stress built up on the other side by measuring the current, then you can measure the shear modulus. Okay? And if they measure the shear modulus as function of temperature, they found the increase in the shear modulus as well. You have a temperature-dependent elastic modulus change. So it looks like very simple, since we can explain those anomalous reduction in the resonant period with just simple classical idea of shear modulus stiffening. Why is that simple? The shear modulus stiffening, you can explain those things without invoking the superfluidity. Okay? Shear modulus, well, as we all know, dislocations are sweeping souls. So if you have dislocation motion in the solid, right, then you have softness solid. However, at very low temperature, the motion of dislocations are pinned by the impurity binding on the dislocations, right? So the Shell modulus increases at low temperature. But this is thermally activated process. If you increase the temperature, then the impurities binding on these dislocations evaporate and then again soften solid. That's why you have stiffen at low temperature and soften at high temperature of solid here. Okay? And this kind of temperature dependence can be explained by simple, like classical idea first proposed by Grant and Liquid, without invoking the superfluidity. So now, I can ask the question again. So is this end of supersolidity? Oh, wonderful. But from the beginning, I didn't believe that explanation. The reason is very simple. Okay? Even though this experiment possibly explained my second torsional oscillator experiment, however, the first torsional oscillator experiment has been done with solid helium confined in porous geometry. Elastic modulus change doesn't affect at all on that measurement. Okay? However, people try to associate this shear modulus with torsional oscillator experiment. That's why I had to do some other experiment to find more solid and firm supporting evidence. That's why I did two experiments, not just only one. First one is rotating solid helium. Rotation for the elastic modulus is quite simple. It's not very difficult if you think about that, right? If you rotate solid helium sufficiently slow enough, think about that. There is nothing changing, right? Just change the frame from the rest to the rotation. There's one exception, just centrifugal acceleration, okay? However, if you rotate slow enough, that centrifugal acceleration will be negligible, okay? However, the story is completely different when you have a superfluid. Even with very slow rotation, you can destroy the phase coherence of superfluid, okay? And because of destruction of phase coherence, you have this kind of vortex cores appear, which is non-superfluid, appears in the superfluid system. And these quantized vortices are imaged earlier in solid helium form and also in the Bose condensed alkali gases. So this is the density profile of Bose condensed alkali gas. When you increase the rotation velocity, this is density minimum, which corresponds to the vortex core, means normal. Okay, when you increase the rotation velocity, the number of quantized vortices increases and eventually destroy the superfluidity. Okay? And similarly, in helium 4, you have, depending on the rotation speed, you have a single core, 2, 3, 4. They did the experiment almost 13 or something like that. So from this experiment, what we know is rotation may influence on the superfluidity, but not on the elastic modulus. Okay? We know the difference. So then, why don't we do the experiment with the solid helium? Okay? Very simple idea. So, but not just only one, not just torsional oscillator response and shear modulus. Do the simultaneous measurement. Okay? So we designed a very special torsional oscillator. So we put the pair of PGT inside the torsion cell. Okay? In this way, I can measure the torsional oscillator response at the same time with shear modulus change. And bring these things and all the instruments together to the Japan. Because there are only 4 rotating cloud states in the world, and not in Korea, unfortunately. And we did an experiment, put those torsional oscillators on the rotating cloud state, and this is a movie of the rotating, whatever. Let's see. rotating cryostat. This is just part of the rotating cryostat. 2/3 of this rotating cryostat is on the bottom. Okay, it's really well-constructed system. So if you measure the vibration amplitude as functional frequency spectrum, you can see the typical resonant frequency of torsional oscillator that we made the measurement is about 1 kilohertz, and the vibration amplitude at this 1 kilohertz is less than nanometer. So it's really quiet rotating cryostat. So we have done the experiment. So what happened to the show models? Let's start talking about the experimental result from show model. As you know, I told you we don't expect any change in the elastic modulus because we just change the frame from the rest to the rotation, and the rotation speed is sufficiently small enough, but we don't expect any change. And this is the result. Sorry, this is the result. Shear modulus as function of temperature, and this is a phase shift which is proportional to the energy dissipation, okay, as function of temperature. So we have single curve. No, we have 4 different values like rotation speed and measure the shear modulus. There is no change as we expected, right? No change. However, I want to be really careful. Okay, I'm really careful experimentalist. Maybe since we measure the shear modulus at the center, the rotation effect is too small to have any like observable change. That's why what I did is I generate acoustic resonance in the torsion cells. Okay, and this acoustic shear resonance is also very sensitive to the change of elastic property. And as you can see from this shear resonance mode, this is very sensitive to the soaring helium in the annular channel. And we did the experiment again from 0 rotation and increased the rotation speed about up to 4 radians per second. Do the experiment again. As you can see, this is just single curve, no change, as we expect. Okay, since the 4 radians per second is too small to have any change in the elastic modulus. Then how about in the torsional oscillator response? Okay, if the torsional oscillator response is due to the elastic modulus change, we don't expect any change in the torsional oscillator response as well, right? So who said you don't believe the supersolid? Let me show you. Here is the experimental result. Okay? With DC rotation, there is strong suppression in the non-classical rotational inertia, means disruption of supersolidity. With just this sufficiently slow rotation, it is extremely difficult to understand this kind of phenomenon without using superfluidity. Okay? And this is the energy dissipation as function of temperature. The reason that I show you here is this dissipation dependence, the effect of rotation to the dissipation is very different from the AC. Okay? As I told you, if you increase the AC oscillation, you can suppress this non-classical rotation inertia at the same time dissipation as well. However, here is the opposite. If you increase the DC rotation, then you increase energy dissipation as well. We don't completely understand what is the reason for this. However, this is probably related with the injected quantized vortices into the system interplay with some residual vortices in our solar here. Maybe not. Another difference coming from the critical velocity. So if you use the AC oscillation, you can suppress the non-classical rotational inertia like that. Okay. However, the critical velocity showing this kind of suppression is 2 orders magnitude smaller than DC rotation induced suppression. Okay, so AC and DC is quite different. Another very interesting features. We set the temperature at 15 millikelvin and decrease the DC rotation speed continuously to 0 and then increase back again. And the red one is the resonant period, okay? The reduction in the resonant period, as I told you, corresponds to the non-classical rotational inertia. So when you decrease the DC rotation, there is increase in the non-classical rotational inertia. The blue one is amplitude. Interestingly enough, the change is not monotonic. I'm the only one to find this kind of periodicity or staircase-like structures. It's very interesting. We don't really know what is the origin for this kind of structures. Maybe the existence of quantized vortices in the solid helium. I'm not quite sure. But this is very interesting observation. That's why we systematically study this behavior at various temperatures. First of all, what we found that, sorry, I forgot to explain what. When you increase the DC rotation back, right, there is no change in the resonant period. Once you go back to the minimum state, then even at the minimum state, even you increase the DC rotation, you cannot destroy. And that's the hysteresis. And this kind of hysteresis is prominent at below about 50 millikelvin. It's greater and greater when you decrease the temperatures. And staircase-like structures persist all the way up to about 100 millikelvin. Above the onset of transition, there is no features, no staircase-like structure. These structures only appear with the existence of non-classical rotational inertia. Okay? And another interesting thing is small spikes in between or in the middle of step. And this is not the noise. Okay, not at all. It's completely reproducible. If you do it 100 times, it's just always there at the exactly same point. It's quite interesting. What is the origin for that? I really don't know, but if you take a look, it is like more prominent at high temperature, and lower temperature is less prominent. And if you do the velocity sweep, decreasing DC velocity, increasing AC velocity, this is much smaller with increasing DC velocity scale. So we don't really know what is going on with these spikes and staircase-like structures and so on. However, probably one can, well, not me or Phil Anderson says, there must be some sort of relation between the residual vortices, which can be excited by AC oscillation, and interplay with DC quantized vortices, injection of quantized vortices induced by DC rotation. Maybe that's true, maybe not. Okay, I told you I did 2 experiments. As I told you, I'm really hardworking experimentalist. I'm not satisfied with the first experiment. That's why I did a second experiment. What I have done is I simultaneously measured the shear modulus and non-classical rotational inertia, the torsional oscillator response at the same time. Okay? So this is the torsion cell. Here, instead of planar PGT, I use the concentric PGT. So I measure the solid helium all in the animal channel. Okay? And also at the same time, I can do the torsional oscillator experiment. And this is the result. If both phenomena, the shear modulus change and torsional oscillator response, coming from the same microscopic origin, what's going to happen? If you change one of the properties, okay, then you expect same change in the other properties, right? This is the same cell, simultaneous measurement. As I told you, using AC oscillation velocity, you can suppress non-classical rotational inertia, right? Here, we suppress almost 90% of that, okay? Then measure, at the same time, the shear modulus. No change. Interesting. Or maybe obvious from the DC rotation experiment. However, well, I'm not satisfied enough. So I just did the measurement in the opposite way. Okay, other way around. This case, I changed the shear modulus by shaking the shear transducer really hard. Okay, make it softer. So the shear modulus suppressed like 60%. Any change in the non-classical rotational inertia? No obvious change. So, and if you plot this change in the NCRI and change in the shear modulus as function of AC velocity or shear stress level, then the clinical stress is very different. They cannot be the same. They cannot have the same microscopic orders. Okay, this end of my talk. As I told you or emphasized from the beginning, I think we have a strong evidence of the existence of supersolidity, and that shows thermodynamic signatures and also drag DC flow. However, maybe fortunately, maybe unfortunately, there are also some other experimental results which cannot be understood by simple conventional superfluid theory. So maybe supersolid is very different from superfluid. So there are a lot of work that I need to do. Thank you for your attention.
Yeah, thank you very much for your very nice and very interesting talk. So is there any question to our speaker?
Yes.
So you mentioned in passing Rittner and Revy. How do you explain the annealing effect or its absence in the case of everything you showed us versus what they found?
Okay, the annealing effect is actually, so when you anneal the solids, helium cycle at very high temperatures, right? There are several arguments about that. First of all, the annealing effect only seen by Rittner and Revy. Other people, well, maybe there is other experimental challenges. They fail to observe those kind of annealing effects. So let's believe the annealing effect from the beginning. Then, I mean, if you increase the temperature to a certain point and then cooling down, you end up being have different pressure. So can I say, is this a same sample or different sample? If it is different sample, what's different? Maybe the density of defect, maybe some other things. So, as I told you earlier, probably for the existence of non-classical rotational inertia, that's intrinsic property of solid helium. However, the fraction of total non-classical rotational inertia maybe dependent on that defect level or density of defect, maybe could be changed from the annealing effect and so on. But I mean, if you want to answer to that kind of question, definitely I need to have microscopic explanation for those supersolidity. For now, I don't have. Okay. Is that answer to your question?
Sorry.
Okay. Other questions? Then?
Yes, please.
Yes.
Yes, I wonder, would it be possible to simultaneously measure the heat capacity and the mechanic properties?
It is quite tough experiment, but I'm planning to do it. I have some idea. Think about it. Usually when you measure the heat capacity, you have to thermally isolate those cells, right, from other things. However, if you want to do the torsional oscillator experiment, it has a strong contact. Right, thermal contact to the mixing channel. So you have to compromise. Somehow you need to invent very clever heat switch. Turn it off when you do the heat capacity measurement. Turn it on when you do the torsional oscillator experiment, something like that. I'm planning to do it. I think that's possible. Yes?
Yeah, please.
You mentioned other explanations of torsion oscillator results and papers by recent papers, for example, by Ripley 2010 Bureau. So you also mentioned direct current experiments at UMass, which make very strong case. What I would like to ask you, so I didn't follow literature closely, and just would like if you could update me. the DEC experiments, which this Remus sandwich. So are they consistent in terms of basic characteristics like superfluid fraction, TC, etc., distortion oscillator experiments?
No. There is a huge gap, order of magnitude difference between the superfluid density, which is non-classical rotational inertial fraction. In terms of their calculation, that's about 1,000 times smaller superfluid density in the DC flow experiment. But I mean, there are other arguments as well. I mean, somehow the non-classical rotational inertial fraction is strongly dependent on the sample geometry and so on. Okay, and you have a very small, like, superfluid density if you have a large cell, and the superfluid UMass sandwich, they have a large cell, and that's why probably that could be explained by that kind of geometrical difference between the torsion oscillator experiment and their experiment. But you're right, definitely, I mean, there is a great difference between non-classical rotational inertial fraction measured by torsional oscillator and calculated from DC rotation. DC flow measurement. Okay.
Any more questions or comments?
Okay.
Maybe the last question. So all these experiments were for oscillating rotation. Could you explain to me, I know very little about this, why you cannot just oscillate it in transverse in one dimension? Do you know?
One dimension experiment? This is because the amplitude of oscillation is pretty small. It's almost one dimension. It's twisting back and forth. Okay?
But is it important that you rotate, or is it not important that you rotate?
Rotation effect is very different from the oscillation effect. Right? I try to emphasize on that. The measurement.
Okay, any more questions?
Oh, now I got your question actually. So you think AC oscillation, is it different from the DC rotation, right? That's your question?
No, not
that.
that.
Okay, fine. We can talk about it later.
This or like that?
Oh.
Yeah.
Not sure. But I mean, as I told you, since the oscillation amplitude is very small, we can do it. I don't see the difference between this measurement and this.
Okay. That was.
Any more questions or comments? I have a question. Is there any application for our light?
I'm sorry. I got this kind of questions a lot, but I mean, unfortunately, there is no application. I should admit that.
Or maybe in the future.
Maybe 100 years later. I'm not sure.
But anyway, it's a very interesting research.
Okay.
Okay, so then let's thank to our speaker again.